In the previous video, we saw the how to draw the asymptotic plot for the Singapore at the origin, Singapore at the origin, multiple poles and digital at the origin, simple pole and the zero on the red axis, multiple poles and the zero on the red axis, and the phase angle of each and every frequency concentrations. In this lecture, we will see the quadratic fractals. That is a complex conjugate poles, complex conjugate zeros, and how to draw the asymptotic Bode plot, magnitude Bode plot, and then phase Bode plot for the poles and the zeros. Are you aware about the characteristic equation of the standard form of the second order system? That is a s square plus twice zeta omega ns plus omega n square. And this is the standard form of the second order systems. That converts this into the form of the time constant form, that is a 1 plus j into the omega divided by the omega n square. This is derived by taken the common term, that is omega n square outside, and then we get 1 plus y zeta j omega upon this omega n. And then our aim is calculate the log magnitude of this complex conjugate poles, or this is the quadratic factor. Here you can calculate the log magnitude, that is a 20 log magnitude of this. You see the log magnitude, that is a 20 log 1 upon. If you consider this integrator as a derivative, we get the minus. We get the minus is the term, that is a minus 20 into this log under root real square plus imaginary square. This is the real term, this is the imaginary term. That is a magnitude equals the under root real square plus imaginary square. Then use the again asymptotic approximations, means at low frequencies and at high frequencies. The asymptotic approximation for low frequencies, that omega is less than omega n, then omega is less than omega n. This is a term is multiplied with the value of the zeta. The value of the zeta is less than 1 greater than 0. That is lies between 0 and 1. You take the magnitude, log magnitude for the log frequency, you will get the 0 dB, that is a minus 20 log 1. Log 1 is 0, minus 20 log 1 is equal to 0. At high frequency, if you see at high frequency, omega upon this omega n is greater than 1 at high frequencies. This frequency is high, then the magnitude, log magnitude of this quadratic factor is minus 20 log omega divided by omega square divided by omega n square. Means if you take the 2 multiply by this 20, you will get this minus 40 log omega divided by omega n. Then if you compare these two equations at the time of the comparing, that is at minus 20 log 1 is equals this minus 20 log omega upon this omega n. That is a corner. If you see again the corner frequencies, that is a corner frequencies, that is log 1, log, if you see, that is log 1 equals this omega divided by this omega n, then omega divided by this omega n square, or this omega square divided by this omega n square. If you, that is the log of here is a log of this omega divided by omega n bracket square. By comparing these two equations, if you compare these two equations, one equal to this omega upon this omega n square, means that is omega equals this omega n, and this omega n is known as your the corner frequency. That is the omega n equal to the omega n equal to the omega c equal to this omega p. This is your the corner frequency. At this corner frequency, slope changes with minus 40 dB, because the 2 multiplied by this minus 20 will get the minus 40, and hence the slope is equal to minus 40 dB, and then corner frequencies for the quadratic factor equal to this omega n equal to this omega c. Here this is the corner frequency. Then that is from the above, it is seen that error is a function of the zeta. That is value of the zeta lies between 0 to this 1. And hence the error versus the omega upon omega n curves for the different values of the zeta are plotted in figure 726. This is a 7.7 point. This 26, that is 7.26 is the plot for the different values of the values of the zeta. Here for the value of the zeta lies between 0 to 1. The zeta is equal to say 0.05, 0.1, 0.2, 0.3. As the value of the zeta increases towards this one, then magnitude gets decreases. The slope is minus 40 dB per decade. Again, the phase angle for the quadratic factor or the complex conjugate poles varies from the 0 degrees towards this minus 180 degrees. That is the reaches towards this negative side. Here is again, this is the error in dB, error factor. Error factor, this is the pole. The pole, the error factor is again varies between the 0 to minus 3. This is for the quadratic factor. The phase angle, that is a pi equals minus pi minus, because this is the integral term. This is the integral term, and hence this term is considered as a derivative in the numerator. Then we will get the minus tan inverse imaginary part divided by the real part. Then put the value of the omega is equal to 0, 1, 2, 3 up to the infinity plus infinity, then calculate its phase angle. Again, draw this phase angle in degrees, phase angle in degrees against the frequency logarithmic scale. That is, conclusion is that if the open loop transfer function in the quadratic factor, in terms of the quadratic factor, the complex conjugate rules or the complex conjugate choose are converted into the time constant form, and then consider the corner frequency equal to the break frequency equal to this omega n. This is a very important for this quadratic. Then what is the general procedure for constructing the Bode plot? At the beginning of the video lecture of the Bode 1, already said, consider the open transfer function of the system. Then convert the open transfer function in terms of the sinusoid just by replacing s is equal to the j omega. Rewrite into the sinusoidal transfer function. Then as a product of basic factors in time constant form as discussed above. converts into the sinusoidal form, which S is equal to the j omega. It converts in terms of the time constant form. That's the time constant form of the system is nothing but that is a 1. That is a time constant form. That is a 1 plus ST1. 1. Similarly, in case of the poles of the denominator, 1 plus STA, STB, that is converts is happening into 1 plus 1 is known as the time constant form. Identify the corner frequencies. Again, corner frequencies associated with each one of these basic factors. At basic level, at least you should draw the approximate this magnitude for the magnitude for the plot. That is a corner frequencies. Already discussed the corner frequencies and then error. That's corner frequencies associated with each one of these basic factors. That is corner frequencies. Is nothing but the slope changes at each corner frequency, that's omega c equal to the minus 20 dB per decade, or the omega c is equal to the plus 20 dB per decade, or the plus minus 40 dB per decade. Identify the corner frequencies associated with each one of these basic factors. Then we may draw the basic factors is nothing but such type of the plot is known as an asymptotic plot. Then knowing the corner frequency, draw the asymptotic magnitude plot. Asymptotic, just you may draw the asymptote at each corner frequency based on their the poles, locations of the poles and the zeros. Then apply the correction factor from the error graph of the figure 7 to determine the correction to be applied to the asymptotic plot. Once you draw the asymptotic plot, then once you do the asymptotic, then start the adding. That is the most important advantage of the plot. The multiplied factors are converted into the additive. Starting from the origin, then add the first factor is added with second, second with third, third with fourth, and up to the last term. Add all the factors. Then apply the error correction. Error correction. At least you should draw the magnitude Bode. This is known as a asymptotic magnitude Bode. Asymptotic magnitude Bode. The error corrections in itself it's okay because the error correction factor is applied at the time of designing the compensators. Then there is error graph. Error graph that is already said the plus 3 dB and minus 3 dB. Plus 3 dB go up if there is a zero. Minus 3 dB at each corner will go downward if there is a pole. That is plus 3 dB, minus 3 dB for the zeros and the pole respectively. Then draw a smooth curve to the corrected points such that it is asymptotic to the line segment. Already discussed that is a dotted lines. Dotted lines indicates that this is the resultant of the exact plot. Draw a smooth curve through the corrected. Then calculate the total phase angle. Total, that's a phi is the phase angle of the open loop transfer function. That's a phi equals tan inverse imaginary divided by the real of the numerator minus tan inverse imaginary divided by the real of the denominator. Then put the value of the omega is equal to say 0.1, 0.2, 1, 2, 5, then 10, 20, 50, 100. They calculate the phase angle for each and every frequencies, and then draw a phase angle plot logarithmic scale. That is, calculate the total phase angle at different frequencies and plot the resultant phase plot. Then determination of the gain margin and phase margin. At the beginning of this correlation, we discuss the frequency design specifications. That is UR. UR is normalized variable. Omega R normalized resonant frequencies. FR, that is a resonant peak. WB or the UB. WB is the bandwidth. These are the three frequency design specifications, and the other two frequency design specifications are the gain margin and the phase margin. The gain margin and the phase margin is a very important in the frequency response analysis to check whether the system is pure control system is stable or unstable. That is the gain margin and phase margin. Both are positive. They say that the system is said to be stable. Here, if you then that is the procedure already discussed. That is draw the asymptotes, then draw the magnitude plot, or if possible, then draw the exact plot. Once you know the magnitude Bode plot, phase Bode plot, then calculate the gain margin and phase margin. Gain crossover frequency. Then on the Bode plot, gain crossover frequency is defined as the frequency at which the resultant magnitude plot crosses the zero dB line. This is the this is known as a gain crossover frequency. This is gain crossover frequency. This is the gain crossover frequency. It is a frequency at which the magnitude is equal to zero. Phase crossover frequency. This is the magnitude Bode plot. This is the phase angle Bode plot. They determine the gain crossover frequency. Determine the phase crossover frequency. Phase crossover frequency, it is the frequency at which the phase angle equals the minus 180 degrees. This is the definition of gain crossover frequency and the phase crossover frequency. Is defined as the frequency at which the resultant magnitude plot crosses the zero dB line. Phase crossover frequency defined as the frequency at which the resultant phase plot crosses the minus 180 degree line. The difference between the zero dB line and the resultant magnitude plot at the phase crossover frequency gives the gain margin. That is gain margin. If you see the GM and the PM, the PM is very important in the frequency response analysis to check whether the given system is stable or unstable. That is GM. GM equals 0 minus resultant magnitude in dB at the phase crossover frequency. GM is negative of the magnitude in dB at the phase crossover frequency. PM is the difference between the resultant phase plot and the minus 180 degrees line at the gain crossover frequency. Give the phase margin. That's a PM equals resultant phase in degree at gain crossover frequency minus of minus 180 degrees. That is a phase plus 180 degrees. This is the GM and then PM. Here if you also have the C, the gain crossover frequency, then this is the phase crossover frequency. That is a gain crossover frequency. Then here is a phase crossover frequencies. That is a gain crossover frequency crosses the zero dB line. And the phase crossover frequency crosses the phase minus 180 degrees phase. Then gain margin and then phase margin. That is a gain margin. That is a difference. This is known as the phase margin. This is known as the gain margin. Phase margin equal to this phi plus 180 degrees. Here is the gain margin is equal to 0 minus of this. That is a minus magnitude in degrees. We will get the gain margin. The gain margin and the phase margin both are positive, then say that the system is said to be stable. If you observe, this is the stable region. That is, this is the stable region or intersects on the magnitude curve at phase crossover positive gain margin. There is the positive gain margin. Then unstable region for intersects on the magnitude curve at phase crossover negative gain margin. There is a, here is a negative gain margin. Here is a positive gain margin. Below the zero line, below the zero dB line is positive gain margin. Above the zero dB line, negative gain margin. So here if you observe next a phase margin, again positive gain margin. Above this minus 1 degrees and then below this is the negative phase margin. Here this is the GM and then PM. What to do at the time of this sketching in the magnitude Bode plot and then phase Bode plot, you may draw the magnitude plot, you may draw the phase Bode plot, and then determine the gain crossover frequency or mark the gain crossover frequency, phase crossover frequency, extend the lines up and then down. That is a gain cross frequency line in the downward, phase crossover frequency in the upward. Measure their gain margin and then phase margin and check whether the gain margin and the phase margin are positive or the negative. If it is positive, then say that the system is said to be stable. The ideally gain margin, if you refer the control system manual by the Nagaragrupa, gain margin, ideal gain margin is 60 degrees, phase margin is minus 30 to minus 60 degrees. Then relative stability related to this slope of the log magnitude. That is a relative stability means all the roots of a characteristic equation are more negative, then say that the system is said to be stable. That is all the roots of the characteristic equation are away from the origin. In addition to the GRPM MR as a relative stability measure, the slope of the magnitude of the Bode plot or the loop transfer function at the gain crossover also gives the qualitative indication of the relative stability of the closed loop system. That is a GM, PM, and then MR. This gives the more stable systems. Then, what are the advantages and the disadvantages of the Bode plot compared to the Nyquist plot? Nyquist we'll see later on. That is the Nyquist plot is nothing but it is a plot of the magnitude against this phase. Once you know the polar plot, uh, if you draw the polar plot and take the mirror image of the polar plot is nothing but Nyquist plot. The Nyquist plot is again used to measure the given system is stable or unstable. Then advantages and disadvantages of the Bode plot compared to the Nyquist plot. The approximate Bode plot can be drawn very quickly because you know the magnitude, you know the phase. Then approximate Bode plot means first for the asymptote, that is asymptote at each convergent frequency. Then take the addition, we get the approximate Bode plot. Then gain crossover frequency, phase crossover, which is gain margin and phase margin are more easily determined on the Bode plot than from the Nyquist plot. In this previous slides already discussed how to calculate the gain crossover frequency, phase crossover frequency, then measure the gain margin and then phase margin, and then comments on stability. Then for design purposes, the effects of adding controllers and their parameters are more easily visualized on the Bode plot than on the Nyquist plot. That is at the time of designing the controllers, time of designing the compensators, Bode plot is easily implemented as compared to the Nyquist plot. Then what is the disadvantage? The gain margin is positive and the system is stable if the magnitude of the transfer function at the phase crossover is negative in degree. That is, the gain margin is measured below the 0 dB axis. In the previous slides already Said the gain margin below the 0 degree axis, then the system is stable. If the gain margin is measured above the 0 degree axis, the gain margin is negative and the system is unstable. That is the gain margin GM below the 0 degree. Say that the system is stable, otherwise this is unstable. Similarly, the phase margin is positive and system is stable if the phase angle of the G of omega is greater than minus 180 degrees at the gain crossing. That is, a phase margin is measured above the minus 180 degrees. Above the minus, they are opposite. GM below the 0 degree, then phase margin measured above this minus 180 degrees. The system is said to be stable, otherwise, system is unstable. This is the determination of this GM and the PM. Then some of this frequency domain specification already discussed the FDS, that is a frequency domain specifications of the system, that is a normalized transitional frequencies, then normalized resonant frequencies, then a resonant peak. There is the frequency domain. These are the frequency domain specification. At the time of designing the any control system in frequency domain, consider the design specification, that is a resonant peak MR. Then consider the resonant frequency omega R, then bandwidth omega T already derived, then cutoff rate, then gain margin, and then phase margin. These are the frequency domain specifications. There is a frequency domain specification, that MR. MR means the maximum peak, maximum value, or the maximum magnitude, or the maximum amplitude at omega is equal to say omega r. This is known as the resonant peak MR. The resonance peak MR is the maximum value of M, the magnitude of the closure frequency response. The large resonance peak response, the large also in transit response. Then second is the again the there is a resonant frequency. That is the frequency, resonant frequency is the frequency at which the resonant peak MR occurs. That is MR. They are the correlate to each other. That is the resonant peak, maximum peak at omega is equal to omega r. The maximum peak, the frequency at which the maximum peak is known as the resonant frequency. You know the bandwidth. Bandwidth means the range of frequency over which the magnitude is greater than or equal to this 0.707 is known as the bandwidth. Here, the next is the cutoff rate. Cutoff cutoff rate. The cutoff rate is the slope of the log magnitude curve near the cutoff frequency. Cutoff rate. Cutoff rate indicates the ability of the system to distinguish the signal from the noise. Then fifth is the gain margin and then phase margin. You know the gain margin. There is gain margin and phase margin measures of relative stability of the system and are related to the closeness of the closed loop poles to the omega axis. The GM and then gain margin and then phase margin. These are the high frequency design specification used in control system if you want to design the control system in the frequency frequency domain. Then the next lecture we will see some simple examples of the Bode plot for the type 0, type 1, type 2 system.